and having me over here. It's really wonderful, and Professor Shri over here. So I learned my UHPC from him. So I'm giving a lecture here on UHPC, but he could probably tell a lot more things to you. And meeting after a long time since 2018, since we met in Mumbai, Professor Sengupta. And thanks for all of you to be here. So yeah, somewhere around 2016, as the story goes, I was starting to look at what next, and what's that thing that could be a game changer, what's that thing that could, because I was always kind of pro-innovation, trying to look at new things. And it so happened that I just came across UHPC and I started digging into it. The more I dug into it, it became, more interesting. And I wrote an email after a long time to Professor Shri, because I knew him from my master's time. And I wrote an email to him that, how does this material sound, or what is it about? I'm trying to look into it. And then came the surprise. Professor Shri said, "Oh, Satish, we are working on this material for a long time now after you left." And, so, and the first US symposium was supposed to happen right then in 2016, June. So he called me over, I went there, and then it strengthened my resolve to dive into UHPC. It also strengthened my resolve to get a PhD as well. So I started off post that. So that was mainly in structures, but right at the same point of time, we dived into material in India. We opened up a research lab and started experimenting. So everything was a scratch. None of us involved were material engineers. We were all structural engineers trying to develop material. So that itself was a process on its own. And the other important process was, once it took about a year to make it in the lab, and then how do you actually bring it out into the market? That was a totally different dynamics. So it took another year and a half, 2 years to actually make it, possible. I mean, this material that could go out in the right sense in the market.
You got the trademark registered, or?
Yes.
Okay, because it's a common name.
Well, yeah, but we have UHPC India as the India as the trademark, not UHPC. Yeah, I couldn't try to do that. So there's the story, and then we started implementing projects. Got our first project right after the COVID, in February 2021, and since then I've been involved in a variety of buildings and bridge projects as well. But what is more interesting is today we see UHPC as a lot more than just a bridge element material or a building element material. I think there's a lot of scope in repair, rehab, impact solutions, high impact solutions, in the marine, underground marine rehabilitation. Subsea rehabilitation. We are providing materials for those. So if anybody is coming over to Mumbai, would, please feel free to get in touch with me. We have a very nice research and development center.
HVDC cables? HVDC, high voltage director, subsea.
Well, not tried that. Not tried that. So here I'm, just going to share some experience as to what we do with precast, and not just precast. We do a lot of cast in place also, but the topic here is precast. So we'll revolve more around the precast today. So the way I would like to start, and why UHPC has, over the last few years become a little bit popular when it comes to problem solving and adding value to projects. When we think of precast, we generally think concrete. I mean, that is what we think about. But when we look at building materials, there are several building materials. I mean, there's timber, there is masonry. Of course, timber is not something we precast. Masonry is also, it is precast, but in blocks. but not in the whole sense of a structural element. Well, we talk about structural steel, right? Nobody talks about structural steel as precast, but it is precast because it is molten, it is poured into, the shape. Actually, structural steel is precast in that sense. Concrete by its very nature has, coarse aggregates into it. Concrete could be something that you need to vibrate, or you could have self-compacting concrete, and so it could be precast one way or the other. But why I brought structural steel into this discussion over here is because structural steel looks very uniform in its molten form and as a liquid and can be poured, and you get very, very fine sections out of it. So is this material UHPC, because it doesn't contain coarse aggregates. Typically, it's all fine aggregates. And so it's a mortar. I don't like to call it as concrete, although UHPC is ultra high performance concrete, but more or less it is a fibrous composite mortar. And that is what it is. And very, very flowable. So I start this slide here showing, this is what is a typical flow test on a UHPC. And it can flow into any kind of mold, any shape that you desire, and it gives quite a bit of flexibility in that manner. And you can see that over here, and this has fibers. This has an enormous amount of fibers. I mean, at least 2% by volume, which is about 156 kgs a cubic meter of very fine, microfine fibers in it. But that's where it comes, close to structural steel. Is one thing that it appears as liquid as it could, and it could flow into any kind of system there is. I want to show you this shape. That is a beam. It's a 14-meter beam, precast beam. And this beam has come into that shape because of several architectural requirements, because of MEP requirements into a building project. And I'll explore more into that we could solve this problem that was there with UHPC, because we could come out with a section such as this. It had precast slabs as well. And I would talk a little bit more about it later. But I just wanted to impress upon the fact, while there are huge bridge girders, etc., that are made with UHPC today around the world, but as sleek as a section this is for building purposes and long enough, 14 meters, how does this work? And it could be made into this shape and size as it is. So we'll come to this. But that's the beauty that we're talking about. Now, this particular slide is very commonly available over the internet, but it is a very, very impressive slide. It kind of shows you where you stand with concrete and pre-stressed concrete, and where you stand between steel and UHPC out there. And that's the beauty that UHPC brings about. Now, when you look at it, it is also impressive that you can carve out these areas out of UHPC. That's what it makes UHPC lighter. A typical UHPC, pre-tension UHPC beam would be about 60% lighter than your pre-stressed concrete beam. And that is because of the properties of UHPC. So we'll talk a little bit about it. We'll impress upon that a little bit so that we understand why we can come close to this. Believe it or not, then it's not just about the materials, but this kind of section then helps in constructability as well, because your craneage capacity, that goes lower. So that helps. Overall, your foundations can go down, or overall your earthquake loads can go down. So there are various associated parameters, that UHPC can bring into place. But
what about corrosion resistance?
Yes, we'll come to that as well. There's a slide on that, and we'll definitely talk about that. So, yeah, that is something borrowed from a paper from, Sri Ramality and Professor Sridharan right over here. But big difference. We saw this. Those are the steel fibers. Okay, they're brass coated in nature, about 0.2 millimeters in diameter, right? And generally 13 mm, but we are seeing some 20 mm work also being done in our country right now. So somewhere in between 13 mm and 20 mm. Here's the beauty. This is typically your concrete, right? It will gain some flexural strength or tensile strength, and it will have a brittle failure. But due to the presence of these fibers, you have the strain hardening behavior in UHPC. It's not so much of a strain hardening, you're not gaining strength because it's at 2% right there. But if you start adding 3% by volume fibers, you will probably start seeing that strain hardening over there. And then at that point, probably UHPC is going to be extremely uneconomical to be used. Even at this point, you would not do 100% building in UHPC, it's not going to be viable. You're going to be choosing, selecting as to how you're going to add value to a project and how you're going to solve some projects, problems in the project, and then utilize UHPC appropriately. And this is your toughness, right? This is where you get your energy dissipation as well. And because you have this strain hardening, you could below, as a designer, below your neutral axis, you can utilize that for your capacity, flexural capacity. And when you do that, your reinforcement content automatically reduces as well. I'm not putting a statement over here that you can completely get rid of your reinforcement. It's a designer's choice what kind of permutation combination works for a project. Pre-stressing, rebar, and the fiber contribution over here. So we can always play around with it to get the right solution for the particular application or for the project in general. One thing you'll realize, UHPC is a great friend of pre-stressing. I say that because in general you will know why do we need a compressive strength in a beam of 140 or 150 or 200. What is the need for that? As such, you won't see a direct need for it. But I'll give you a very, very small example over here. If I take concrete and UHPC side by side, I'm going to put some numbers over here in terms of compressive strength, right? 50 MPa right there, and 150 MPa right there. Typically, you would say I get 2/3 of my compressive strength, initial strength, and I can do my post-tensioning or pre-stressing. I can release my pre-stressing, right? So I'll put some number over here. Initial, at the jacking force, you need about 30 MPa right there. Here, to take advantage of UHPC gains early strength, so in 3 days or something like that, you would have 100 MPa right over there. And when you have this, your initial pre-stressing stress that you put, probably about 60% at max, right? At max. So if you put 0.6 of this FCK, you're limited to about 18 MPa right at the initial phase. Whereas 0.6 of UHPC is 60 MPa. So you realize that you can put additional pre-stressing into UHPC. Of course, there are other areas to be looked at in terms of design, but you could go high in terms of an initial stress, and therefore you could go longer, leaner as well. And that's why I just mentioned that pre-stressing is a great friend of UHPC when it comes to long span construction right over there. So this is where the advantage in flexural members come in. When it comes to pure compression members such as a column, it's a direct advantage. It's a very direct advantage in terms of what you can use, right? You have a 50 MPa column versus a 150 MPa column, you're going to get a reduction in size, and There's no, nothing else to look at. So that's a very direct advantage. Elastic modulus is generally high. It's not following the same route as a concrete out there because it doesn't have core segregate. At some point, you're going to be right over there. In typical construction level UHPC. Now, when I say that, that number is not limited to that. There are some special purposes UHPCs out there that can reach 75 GPa or 80 GPa as well in terms of elastic modulus, but those are not the ones which are typically used in construction. Your creep is itself lower. Your creep itself is lower because the way UHPC is designed as a mix, your particle packing is really, really tight. I mean, that is one of the fundamental bases of UHPC. Apart from good quality raw materials and all, the one big fundamental of UHPC is your particle packing has to be so tight so that your voids are lower, right? And so your creep automatically goes down. So with normal curing, you're probably going to be at coefficient of 1 or 1.1 as compared to 2 or 2.2, which is there for concrete. If you go ahead and steam cure your UHPC for 48 hours at 90 degrees Celsius, all even steam curing, it is possible to reach numbers as low as 0.2, 0.3. Okay, which is you're getting to almost nothing, and it's pretty much acting like structural steel out there, right? So that is an advantage that you can get out of steam curing, but then steam curing is expensive as well. You're putting in energy. In today's world of sustainability, green, low carbon, and all of that, you try to put 48 hours of energy into UHPC and steam curing, it kind of works against that, although it helps in certain manners.
90 degrees centigrade is pretty high.
Yeah, 90 degrees centigrade is pretty high out there. So, and the same strain hardening behavior that you see right at the top over there, it helps in improvising the shear behavior tremendously. And even without rebar. Now, well, you look at your concrete code and concrete plus rebar, your tau C max is about 4 MPa. Right? But here, if you look at it, just your design shear strength out of UHPC, the fibrous UHPC, is right at about 10 MPa. So you can have more going for it, but you can get 2.5, 3 times the shear capacity out of that. And that is why, if I go back to the previous slide, I can carve out the rectangle so that all you need is a small web in between, and that is where your flexural members out of UHPC, become way, way lighter. So I hope, at least this slide, by all accounts, is clear. For structural designers, one more thing, your compression curve is no longer parabolic. It is pretty much more or less triangular in nature, and the way you design a UHPC member, a continuous UHPC member, is a little bit on the reverse side. So when you design concrete, you start right from the concrete strain of 0.0035, and then you calculate the strain, in your rebar or pre-stressing and go ahead with it. In UHPC, what you do is you work your way up to the strain localization point. Although here, I have stated 0.007. Those were the early days, Dr. Shri, out there. The 0.007, nowadays, for the last couple of years, I've seen this number being reduced to 0.005 out over here. But you start from here and do your calculations backwards. So that is why you're using a full stress block of UHPC below your neutral axis. So your design starts from here, and then you figure out. Therefore, I've said strain less than 0.002. It is not equal to 0.003, right? So that's philosophy right there in terms of what UHPC is, all about. And that is why you can get sleeker members, and because it is flowable, you can put it, in any kind of shape that you want. Because today with computer programs, you can analyze any kind of shape. It's very easy. Not that you cannot do it by hand, but hand could take a lot of time. But you can come up with variety of shapes, and you can do your analysis pretty fast. You do a section analysis, your results come out very, very fast. And after all those years, I mean, this curve has been there for a long, long time. Then we saw a similar curve. I was at IIT Roorkee. I saw a very similar curve, which was pretty straight. You did the test for us, which was, Dr. Sri Prakash here did test for us 3 years back, maybe 4 years back. It was also pretty straight in that sense. And now we have a nice displacement-based machine that has been set up. So I just thought I would do a test out there. This is per the French code, and you can see we are getting a very straight behavior out of it also. At least there are 3 or 4 examples back at Iowa State University. Also, all the tests that were done with 2% are pretty straightforward, rather than having an increasing curve on the strain hardening. So there are these, I would say this as multiple points of conformations, that with 2% steel fibers, you are pretty much almost flat on your curve right there. So what happens if you just have 1% steel fibers, right? So with 1% steel fibers, I think it's going to be more like a strain softening curve right over here. You're not going to get that strain hardening behavior. Your strain localization happens pretty fast. I don't know what's your take on it. That's what I have seen.
Yeah, well, you need to have at least 1.5–2%. Then only you get that.
Right. So on durability, what happens to corrosion, right? Because the material is so tight, the particle packing is so tight, it automatically, that is why it's called ultra high performance concrete and not ultra high strength concrete, right? If it was just about strength, we would have just called it ultra high strength concrete, right? But you see that, when you oxygen permeability, chloride ion penetration, or any kind of reinforcement corrosion rate or carburation rate, it's a comparison of concrete versus high performance concrete versus UHPC. UHPC is here in blue, right? And it's next to nothing. And that is why, in general, I mean, we are talking of a decent, good UHPC that is there in the market. You can talk about a 100-year maintenance-free structure. So the maintenance-free being the key word. So it's not just 100-year service life. You can achieve a 100-year maintenance-free. So that target can be achieved.
What is the differentiator between high-performance concrete and ultra-high-performance concrete?
Right. So, of course, concrete, again, when we speak of high-performance concrete, could be strength-wise any range, maybe about from 50–55 all the way to 90–95. Again, the coarse aggregates are part of the mix. Fibers are not going to be part of the mix. May not be. Only when it comes to FRC, there could be fibers as part of the mix. Durability wise, high performance concrete is generally very good because we again have the word performance in it, and there are good examples of projects in India where simple RCPT test, if you take, have achieved 500 coulombs or 600 coulombs as well. At UHPC, you would generally be looking at a range anywhere from 50 to 250 coulombs. You're going to get the RCPT values, and therefore it is very tight. So general key differences.
Has the industry made a definition as, like we have some definitions between normal strength concrete, high strength concrete. Similarly, is there any definition for conventional high performance versus ultra high performance?
That's a very good question. I think we should.
There are three parameters. The strength is minimum compressive strength. Different codes define at different times. Strength is 120. They generally it's accepted for streaking correctly. The second thing is the flowability. We do mini flow, so it should flow. So there is no external compaction is required. The third thing is the durability requirement, which is typically measured in terms of your RCT.
Yeah, and the fourth, of course, I would add the post-peak tensile property, the post-peak tensile property in the strain hardening.
Typically 5.5 or 6.
Yeah. So these are the key differentiators as far as the material is concerned, and so it's again a mortar more than a concrete in that sense. So I would now like to take you to the first UHPC project in India and how that came up. I had worked with a cable company some 10-12 years back. So I was able to interact with their managing director quite a bit. And it so happens that at least in India people know of ISKCON. So they are big donors to ISKCON and they are associated. So one fine day, where we were actually looking for projects in UHPC, now that the material was developed, now everything was done, and we were trying to get our first project, got a call out of the blue that Satish, we have a case where the building is up, it's G+2. For ISKCON, we are doing a training center for the in a tribal area. It's a G+2 building. The terrace, the last floor, in fact, we do not want internal columns. We want, instead of 7 meters, we want 14 meter spans. The trick is, we want it in concrete. We do not want structural steel. And the second part of the trick is, we do not want any load increase on the external columns, because it's just G+2, moving from a 7 meter beam to a 14 meter beam, in general would increase the loading on the external columns. So those were the requirements, and I just jumped out of my seat. I said, okay, I have an idea what I could do for you, right? So I met him the next day, and what we did, this was part of a bigger structure out there, but they had these internal small columns. Now we cannot structurally, we can see here that columns are very small, but there was somebody involved, a structural engineer involved at some level inside on the interior areas. But these beams were removed, and what we did is we placed these 14 meter UHPC beams, extremely thin. They were unbonded post-tension. So about 3 strands in there. We additionally, because the first time we were doing something like that, we additionally put in 4 rebars as well, just for safety purposes, nothing more than that. We had enough capacity in there, but we didn't want to take any chance. So we added 4 rebars out there, and we had a very thin web. So this green thing is something that you see. Now, they decided they are going to do a cast in place, slab at that point, right? We said, fine, it's a good one step. You're getting what you need. I can give you a 14 meter clear span. And that is how this started. So even after doing that, with the slab and these beams, the overall reduction on these columns compared to this was 30%. So we reduced the loads actually from what it was supposed to be with the 7 meter spans. So there were just about, I believe 13 or 14 beams that were cast. And let me show you some pictures of it. And we did some other interesting stuff with it. So those are the UHPC beams up there. And I'll show you something interesting we did. Now, the major thing was, what do we do with the encapsulation of the anchors right over there? So we said, okay, we're going to try 2 tricks over there. Number 1, we got everything highly galvanized, the barrel anchor and other things. Second thing, we opened up this end right over here, and this entire region was poured again with UHPC, because UHPC is a highly durable material as such. So we said that this is the extra protection that we are providing. So we did not use any grout per se for closing up the stressing end, but we used UHPC to close up that end. So you can see, the formwork right over there. This was precast on the site itself, and then was lifted up as you see. Weight of the members was just about 4.25 metric tons each. And I just want to show you, because this is for memories, because this is India's very first beam that is being casted in UHPC. So I keep this video all the time, the very, very first one. And you can see that, material is flowing. What were the challenges? We were working in a 40 degrees temperature environment outside. That was the biggest challenge. The first time we mixed UHPC outside, we immediately figured out that we need to take control. Although we were mixing ice and everything, it was fully iced, but we learned a trick immediately that before we start the mixer, we should cool down the mixer by putting ice in it, just ice. Okay, and you run it for 5-10 minutes with quite a bit of ice, cool down the mixer in that environment, and then start mixing UHPC. Is going to have a very positive effect. So that is something we learned from the site, doing the first project in a 40 degrees centigrade environment. This is the second project out there. This is in Mumbai, nicely functioning for the last 3-4 years now. And 8.25 meters in span, nothing big, right? But this does not have pre-stressing. We could have gone with, shallower beams over here, but some discussion with the owner and the architect, I was suggested, why don't we take the HVAC system, the air conditioning system, through the beam at the center, and can we work it out? Oh, actually we ran a nonlinear model in Abacus, checked it out. We did put a couple of extra rebars on all sides of the openings right over there, and the only other rebar that it had was about 3 number 12 dia rebar in the bottom flange, no pre-stressing again, and there was some top rebars, of course, to do the composite connection with the concrete deck. So that was all this was about, and you could see it in place, and that's again very slim out there. There's a question that it's not there in my slide, but it comes time and again during conversations, is what do you do about fire? Because generally if you look at UHPC, even with all the fibers, steel fibers in it, it's so tight that if you put it in a muffle furnace or under fire conditions, you're going to pulverize it. Okay, now that is something which is not right for building systems, right? For a bridge, that will work in general. Anywhere in the world, bridges are done without addition of anything extra other than steel fibers in UHPC. But for building systems, so we ran a lot of tests by adding a bit of polypropylene fibers along with the steel fibers, a very minute bit. So we went one by one, and what we found is, by the time you add 0.2% of PP fibers along with the UHPC, you have excellent fire behavior. Why? Because PP fibers, they melt around 150 to 100 degrees Celsius, and they create these fissures for the steam to escape. So that is why it improves your fire behavior sufficiently.
And Professor Kudru, also propagates this, that mix the fibers.
Correct.
Steel along with polypropylene.
Polypropylene, yeah. So we did a range of experiments. We have a muffle furnace in house, so we did tests for a good 2 to 3 months before coming out with what kind of PP fibers and what volume of PP fibers need to be added to make that happen in building
You
style.
really tweak the mix, but again, still concerns are there. But PP fibers definitely help.
Yeah, I'm just curious, how are you providing the shear content? Is it like a single bar in the web?
Sometimes they are offset this way, sometimes they are double depending on the
Because you are taking a single bar and then turning it around.
turning it around. Yeah. So depending on the web thicknesses, we are sometimes providing double as well. So it's basically a combination, either single or double, depending on the web thicknesses that we are looking at.
Most constraint was anchored with UHPC.
No, the filling of the stressing zone.
So is it the concrete or do you have an access hole or how did you?
Right there, if you could see it in the pic over here, yeah, there was an access hole provided for stressing it.
But you were able to pump UHPC?
Yeah, so we created a little formwork that could attach and we could pour UHPC in there. Yeah.
And this unwanted force tension.
Yes. Just because, I don't know, I have worked so much in the US and have designed a lot of unbonded PT, for multi-story buildings. There is kind of a comfort level in designing unbonded quite a
There
bit.
was no problem in anchorage, no bursting or any issue, nothing happened.
I was so nervous. That was the first UHPC beam being done with such a thin flange. And when the first one was being, I know what care we took. I'll tell you, this was the first one. I was standing nearby itself and I was extremely nervous what was going to happen. So we did 50% stressing first. Then we went back and did the rest of the 50% stressing out there. Nothing happened. All the beams went well.
Is that you also use the mechanical anchors or what, just the UHPC?
Mechanical anchors. Mechanical.
Plus the UHPC
Ye-
goes.
Yes. The reason Professor Sri is asking that question is my entire PhD work is on UHPC anchorages without the use of mechanical anchors. So, but yeah, we use the mechanical anchors right over here too. So, this one was deeper, about 775. It was thin and deep. We didn't have any constraints with respect to that. Yeah, we could come out thinner, shallower as well, shallower and wider. So it's really depends what is acceptable on the site, what works, what is the most, what works out most efficient, economical, and what are the parameters. Could we have done that in 600 mm? Probably yes. It would have, probably we had to put more post-tensioning in it. Probably this would have been thicker. The web might have been slightly wider, than what we had. So it's just a matter of what is more pertinent to that particular project at that particular time.
Okay.
So curing, again, I mentioned that, steam curing is one way, but yes.
Last model, what's the significance of that halo portion?
Oh, that was for AC ducts to go through. So now, when they have the ceiling, they don't have to put the air conditioning ducts below the beams, that eats up more space. So it went through that, and, the ceiling is right along the bottom flange.
Do we get any design advantage with that halo? Usually,
It's at the center, the shear is almost zero. That is why we were able to do that right at the center point, right? Plus, it's a little bit wider. That was a concern. Therefore, we ran some nonlinear failure analyses also to check it out. What is the behavior that we are getting out of it? Okay. But like I mentioned, you can do water curing. I'll tell you, this is with water curing. This is about 84 members cast over 30 days time. The main strength was about 186 MPa on site, and a standard deviation of about 8 MPa. That is what we achieved.
Whenever you are measuring these strengths, are you using the standard cubes or
100 cubes.
100 cubes?
Yes.
Smaller cubes.
Smaller cubes.
Sir, like why do we have a higher standard deviation? Is that depends on the strength of the concrete?
Yeah, I would say, yeah, the standard deviation, yeah, with normal concrete, you might not want to see a 8 MPa standard deviation, but when you're talking of strengths in the range of 150 to 200 MPa, yeah, that number is not big.
Then some material is like all kind of material getting homogeneous. So why do we expect as much of?
See, there are other parameters. It's probably not just about the materials. Even if you get the best IS molds out there are so many situations on the site, how the person is putting the things in there. Are you getting a perfectly 90 degree angle on the cube? Are you getting, are all your levels of the cube really flush, that you don't need to grind anything at all? So there are certain other parameters also that come into place, and so those standard deviations or those numbers are going to be slightly off.
If you want to develop mix for 120, 150, 180 or 200, like are there any standard ranges or standard deviation that I have to use?
So I think we are putting a number in the IRC right now.
Yeah, see, from whatever I'm collecting from Satyasilan and other data,
Yeah,
its standard deviation is anywhere from 5 to 8, as you say.
yeah.
But again, French code asks you to take like 10 megapascal less than
10, yeah.
characters.
Yeah, 10, because you can easily reach that 9, 10. If we do it too tight, believe me, concrete you reject, you're going to be losing 7,000 rupees a cubic meter. This, you're going to be losing a lakh rupees a cubic meter. You cannot be that tight on it. When your, base numbers are still matching, just because of standard deviation, you do not want to reject UHPC out
You
there.
take a lower strength.
Yeah. So what we're trying to see is also from a sustainability angle, we're trying to see if UHPC has to be used more, throughout the country, and from a sustainability angle, can we put the datum as 120 MPa at probably 56 days as well? Okay, not just 28 days. Can we do it at 56 days so that the acceptability grows? The material is more sustainable in that sense, and so now this is another project. So I'm just trying to show you what things are possible. There's another project which is about a 16-meter UHPC beam, but the other beauty here was to construct it faster. This was about 10 meters high, so how to push on your construction on site. RC panels of about 4 meter by 5 meters were cast, and they were put on top, and everything was connected or jointed together with UHPC. Now, stitching with UHPC, I'm going to be spending some time on it, again, a little bit. But if you may, that the beams were first placed, and then these panels were placed. The girders are right over here. The girders are right over there. And then UHPC was poured into these joints, and all the connections were done. And the project was able to move forward really fast in that sense. So I don't know, I don't like to claim it like that, but I still put this. We're trying to do a building in Mumbai. It's about 220 meters high right there, and it's currently about 8 or 9 levels up. But we're trying to see, I'll tell you what we have tried to achieve with UHPC. Number one, I think I made a statement that you don't want to do a full building with UHPC. It's not going to be economically viable. We wanted to find out where UHPC is going to help, if it is going to add any value to the project. So the total amount of UHPC on this project in terms of concrete volume, overall concrete volume, is just about 12%. That is where the break even on the costing was for the building as well. Okay, so the entire UHPC is just about 12% of the total concrete, including the foundation and the basement walls and everything else, right? It's just 12% out there. Now this is a commercial building, about 2 basements plus 56 stories, so about 58 stories high. To the top of the terrace is about 210 meters, another 8-10 meters above that you have, architectural things going. It's a hybrid construction. So the core walls are cast in place going up, whereas the floor system is a precast system. So the floor system, if you see, we have some 10-meter beams over here. The 14-meter beam that I was talking about, okay, at the typical, that is both at the podium levels and the typical levels. The podium level cross section is just a simple rectangle cross section. The typical is the one which is a little bit dicey, and I'll tell you why that is dicey also. But that is 14 meters. And here is something unique. This is a 19-meter thing, but we made it out of concrete, 3 pieces of concrete, and they are stitched together with UHPC to the core walls. So everything is stitched together. It becomes a 19-meter beam. The stitching part is with UHPC. Now, if you look at it, the beauty of UHPC over here is because of UHPC, we have been able to achieve a complete floor, because that's the full office floors plus the corridor. We have been able to achieve a column-free floor, an entire floor that is column-free. Now that in a city like Mumbai is something, a developer would any day prefer from a selling point of view. And of course, big commercial offices, those who buy the big financial companies, etc., they like those kind of things. The second thing that it was helping in is, of course, getting these longer spans of 14 meters and all. The third thing, which was not precast but could be precast, are the columns. If you look at the column sizes are also limited in nature. If this were just a concrete, the column sizes probably would have been more than double of it. So it has really played a role in trying to open up, bring more efficiency to the project. And what we are hoping now, that above the typical levels, we are hoping for that, pushing for that, planning for that. I hope that happens. Is about 4 to 5 days construction cycle will come. So I showed that beam, and I'm going to show that beam again, and I'm going to show you some cross sections of it. This is the corridor right over here, and in that corridor there are various mechanical, electrical and plumbing lines which are going. So what was the prescription to us is that the overall slab plus beam, whatever it is, the overall depth cannot increase over 300 mm. They need the rest of the space for the MEP, and then the space below for the corridor. In the parking zones, that was not a problem, so we just had a straight rectangular beam running through. But at the above levels, that was an issue. One more thing we got to understand is these are all pre-tensioned slabs. So they are all precast pre-tensioned slabs, which we are stitching together with UHPC. Now, generally when you do a precast building, you do a hollow core building, you have the hollow core butting against each other, and therefore you need to have a screed over it of about 3 inches so as to create a continuous diaphragm system that connects through all the shear walls, etc. Now, by doing this joint, we were able to avoid that 3 inches of screed because you have a monolithic construction in place and the diaphragm automatically gets created. So again, the load on the structure was being reduced, and one additional, floor placing, concrete placing activity throughout was taken off. Now let me show that beam again. You see some wings over here, right? You see these wings right over here. Now, why was that necessary? Because we did not want to, shore up the slabs, right? The slab needs to just sit on top of it, top of the beam, and if the slab sits on top of the beam, you're done, basically, and that should work out. We had a situation over here that if the slab sits on top of the beam, I would just have a beam of 100 mm, which is, just not possible, right? So I cannot have a slab of 200 mm and a beam of 100 mm. That is just not possible. So we needed to figure out a way to create connections out there. So what we did, and I'm going to show you sections starting from, I believe, here, section right there at the corridor area, section right here, then I think sections here and right at the end. But before that, let me just show you the design detailing of the beam as well. The post-tension detailing which went into that particular design. I will also show you the connection that we did here at the far end. It was a pinned connection that we created with the beam out there. And if you can see here, we wanted to maintain the UHPC of 300 mm and not have the slab over there, although the slab still needed to be self-supported over the beam. And yeah, so this is how it looked like. That is a top plan. These are both the side views over there. That's at the corridor. So you see the wings over here. The slab comes and bears on the wings, and then you have a jointed connection right over there. And these additional rebars, etc., you have connections to the beam going right in. So this is a fully connected beam section actually to the cross beam over there. This portion was extended out because we needed a transition zone over here. So at that transition zone, the wings are still there. You still have the slabs bearing over the wings, and you have the stitch connection which is happening right there. Then we move on to this, which is the most typical section inside, which is a 500 by 500 section right at the center over there, and still stitch connected to the slabs. And right at the end where the anchorages are there we needed a wider section. So you have this and the similar connection right over there. At the end of the day, we do not have to shore up any slabs in those areas right over there, because that would cause a constructability challenge, and we do not want any constructability challenge. But there are times when you sit down and you have to, a project has to work like a team, and so you have to accommodate all scenarios, whether it is the MEP, architecture, and the structure coming together along with that. At the far end where the pinned connection was there, let me come back. This pinned connection right at that end, and that is designed with an steel embed plate with headed studs inside the beam. There are some detailings of how that went about. So those as the building is getting constructed, we have these at some other locations as well. So those are getting carrying, those are going along on that building. But I mean, what I wanted to show with this is with UHPC, there is a way out to do things without just, not that at every other point you need to dump a column. It was very important for us not to introduce other gravity columns down the middle, because we wanted that gravity load also to go to the core, because the building is slender, tall, and it is seeing a lot of wind force, and you would see tensile stresses, etc. in the shear wall. We wanted as much gravity force that could go into the shear wall. We tried to do that.
But were you able to meet the tolerances? Because even in steel, the embedded plate,
Yeah.
especially particular.
So we kept the tolerances on the sizes of the embed plates and headed plates, so that
most of the time you get complaint that they're not matching, and then you're.
yeah, so we kept some decent tolerances out there, which we knew upfront that these kind of challenges are going to come. So all the good amount of tolerances were provided in those connections. I would like to show this. I mean, this is something typical that you've seen, but also with the shear walls, we were able to provide a stitch connection out there with the shear walls right at the end. This is with the slab to shear wall connections. I'll come to the connections, but before that, just want to show on site, there is a nice 3 cubic meter, twin shaft mixer out there in which UHPC is being made and is being delivered, whether cast in place or to the precast formwork out there. So just wanted to show that is happening on the side, and this is casting of one of the rectangular beams. Sorry, it's sideways out there, but you can see the flowability of the UHPC. So you do not need to vibrate. Now the question comes, what happens if I do vibrate, right? I generally say, please do not vibrate. You want to do some hammering, just touch and go somewhere from the outside, it's fine. But if you do continuous vibrations, you are going to, probably there's a tendency for the steel fibers to align in one direction. So you want the steel fibers to be very randomly distributed. So there is no point in vibration. But you can see here, the UHPC is just flowing inside, the formwork. And so you don't need to do any vibration at all. Now these are the precast slabs which are out there on the project. A complete precasting system has been, or pre-tensioning system has been put into place. That's one of the 14-meter rectangular beams, on site, hanging. This is the 19-meter beam. All right, Dr. Shri, yeah. Hope to catch up with you soon. Yeah. So I mentioned about the concrete beams that were in 3 pieces, because it's not like a bridge project where you have a mega crane, that can come in. Building projects have limitations on the crane capacities and sizes, especially when it's going to go out that tall. So we needed to work within those limits. And then, we have, the stitching was done in these zones out there.
Was there any additional post-tensioning?
There was post-tensioning in this, yes. It was
It's
there.
like a segmental construction. 3 segments,
3 segments, but fully stitched together.
fully stitched, and then on top of it there is post-tensioning.
There is post-tensioning, yes. And it's a very tight site. Our site is here, there's another building going on there, there are at least like 5 or 6 buildings happening, right in the vicinity of each other. You can see the UHPC beams are just, dumped right next to each other in that area. These are UHPC columns, by the way, out there. So yeah, you can see the joint being poured over there on the left side, and then Yeah, this has nothing to do with UHPC, but you can see the UHPC columns over here, and on the background there's this self-climbing formwork that is, going up in the tower. Now to connections. That's another famous photograph from a FHWA publication out there about UHPC connections. Now typically, when you design regular concrete and you're providing your development length or your lap lengths, what is the typical length that you provide? Somewhere from 35 to 50 times the diameter, somewhere in that range depending upon the strength of the concrete. But with UHPC, you hardly actually hear this 15D number comes from the Swiss recommendations. If you look at the FHWA tests that have been done on a variety of direct, tension of rebar, they have pretty much prescribed, even the ASHTO has prescribed. The ASHTO recommendations now prescribe 10 times the diameter. But, here we feel safe to just extend it out to 15D per the Swiss recommendations and go ahead. But ASHTO does provide 10, and you will see that most of the tests have been successful. The FHWA tests, you will see that in 6 to 8 times the diameter, they have been able to develop the entire rebar in UHPC. And hence ASHTO has put a number of 10 times the dia. The Swiss says 15, so we go with 15, but here you can see these are concrete panels over a bridge. The girder, this actually is a steel girder below. There's a steel girder below. And you have all these UHPC connections, to the steel girder and panel to panel. The difference is quite obvious when you do a concrete stitching. You have to develop all your rebar, you need to have wider stitches, versus a UHPC stitch is quite lean and thin, and you can probably make that happen. Coming to this morning's presentation about connections at the foundations. So I didn't have this slide, I just put it during the presentation because I was hearing about, the connections at the foundations with precast and all, so I just pulled it out and I put it right then. But this is also a well-tested UHPC connection. This is a pile cap or a foundation, you can say, where ducts have been left out. You pour UHPC into the ducts. You have a rebar coming, into that foundation, into that duct, and you have your pier or column, whatever you may say, or wall, and you just insert it into it. And that's the simplest connection, which is happening inside the foundation, right there, without the need for grouted couplers or direct couplers.
How would you rate UHPC with respect to the conventional grouts that are being used?
In what
terms of workability and...
Great question, because when we mention grout, this is still UHPC, it's not a grout. This is a flowable UHPC. Even in marine, what we use is slightly more flowable, but it is not like a grout. We are currently in-house working on a UHPC grout that flows more like conventional grouts that can go into the ducts and pre-stressing ducts and all of it. So hopefully in the next 2 to 3 months, we should have that, available.
But I think more with the flow, I think the development length requirement.
Yeah, here the development.
The requirement reduces and also the best in the durability. Durability, definitely this will be better.
So this is a well-tested connection back in the US, and so I thought I would put that in this morning just to showcase a different.
Do you have any additional confinement as well? Close where you have the sleeves.
I don't think there was anything there. I mean, what I remember from reading the literature, there was nothing else out there.
So this sleeves acts like, say, anywhere,
Yeah.
this sleeves acts like a confinement. Whenever there is a trying to pull it out, it cracks
Yeah.
a forming, it acts like a confinement.
This is again, back from the US, where this is New York, where they have a connection to the pier cap, between the pier and the pier cap. If you look closely at this connection, it's not the entire region over here that has to be poured with UHPC. Look closely, the concrete core still comes up. So it is just the periphery that is being poured with UHPC. So you're not pouring a huge amount of UHPC over there. It's just a very small quantity of UHPC that is going into it. There's another example that I would showcase. This is something that we did over the top of the metro projects at the bearing pedestals for Tata projects in Mumbai very recently, wherein they asked us for UHPC and we were able to provide some. So this is right at the bearing plates, right below the bearing plates where UHPC was provided.
You see, compared to this dense reinforcement,
Yeah.
I think conventional concrete is not possible.
Yeah, not possible. Plus, probably that dense reinforcement was not needed with UHPC, but they had everything in place. It was like, the call came, can you provide us UHPC? Okay. When do you need it? Can you provide us tomorrow morning? We want to cast. So, it was that fast. Sorry to put in a cast in place element over here, but just wanted to showcase that when I said UHPC is never going to replace concrete. I think that's a very misinformation which is out there, that UHPC can completely replace concrete or structural steel, something like that. It has its own place as a material. That is where it's going to use. So in this particular project, this was a departmental store, and going up, these center columns, which were predominantly gravity oriented columns only, these center columns in M80 grade concrete, they were coming out to be 1600 by 800. So those, we got it replaced with UHPC at 750 by 750. That is where in a departmental store, the space, the efficiency in the space, etc. comes up. So even in precast, something like that, could be looked at. And yeah, that's the column out there. In fact, I don't have two photographs over here. I just forgot to ask. Right next to this particular building, we did a precast swimming pool between two towers at 70 meters high, and a precast walkway between two towers 70 meters. That would have been nice to show. I will try to pass on some pictures that are completed.
In Mumbai.
In Bombay, yeah. Chembur area. Chembur.
Okay.
Right.
This fancy swimming pools at a rooftop, isn't it creating other problems?
Other problems are there. So bearings, those kind of the seismic bearings, etc., were provided at the ends. So
I know this has become a fashion these days.
right. But yeah, those are troubles in seismic areas. Yeah. So all the bearings were appropriately taken for that particular thing. I do want to show this particular thing. I want to show this for one reason, is UHPC can be pumped. So even if you want to do some precasting or any other work at elevated levels or something, it's not something that cannot be done. Plus, there are a variety of projects where we have made UHPC out of a premix in a transit mixer itself, not any high energy mixer. So a transit mixer was used where a full premix just goes into a transit mixer and goes. But if there are any questions about UHPC doesn't have retention or is it pumpable or anything, I think this particular video is going to help out. And this was done for you can see all those premix bags and transit mixers. There's a pump out there, and the UHPC coming out of the TM into the pump. So back in the US also, Steel-like uses transit mixers to actually provide UHPC at joints and overlays. They do that, even Ductile, after seeing Steel-like, Ductile started that. And you can see that coming out. This is about 60 meters high above the ground level, and you can see the consistency is there. There is no segregation or anything. So it is possible, even if you're doing a bridge girders out there on a, let's say it's a casting yard on a site, and your site plant is a bit away than where your formwork system is. So you can put a pump in and you can push UHPC into the formwork, for your precasting purposes.
See, yesterday we had a presentation by Professor KBM Subramaniam, 3D printing.
Yes.
Now these two can be nicely matched.
Yes.
In fact, there's quite a bits of scope of using UHPC in 3D printing.
Absolutely. I mean, I'm just thinking, just a couple of weeks back, I was in the southwest corner of Germany, where 3D printers, manufacturers of all these things are there. And you could actually see that they are 3D printing against gravity. I mean, the mix that they had was really amazing, that you could work against gravity and print it and still, keep going. It's really amazing. I do want to show, this is a precast segmental girder. A precast segmental girder at the coastal road in Mumbai, which had a bursting at its anchorage. And exactly the same reason, too much rebar, how will concrete go into it? So you would have honeycomb problems, you would have, so if you just look at this is after a lot of things were cut down, but you had amazing amount of rebar in there. There's no way that you could, push concrete properly, and so they had bursting in that region. So
Not Atul Setu.
not Atul Setu, the coastal road, right now, the coastal road, the new coastal road. So Professor Meher Prasad called me up, actually, when this happened, and then you see the center slide, UHPC, I mean, everything was cleaned, and then UHPC was just, poured.
I think what you said, that originally they could have designed using UHPC, they could have reduced
Substantially on that, yes, they could have. So anchorage area, the UHPC goes extremely well. And again, the curing was done just with water right over there. Curing compound, a good curing compound can also be poured. If you have a 90% plus efficiency curing compound, it will do its job pretty well. You don't have to do water curing. And then at the end of the day, the UHPC repair work looked that way, and you could see that they had started stressing it out. So that worked well. Now, coming to the end, I just wanted to show some international pictures. This is in France, southern France, inverted T-beam. Now, what's the beauty of this inverted T-beam? And I realized it a little bit later when I took pictures. I was there. This was 2017. There was a UHP FRC conference in Montpellier, southern France. Dr. Shri was also there. And there was a presentation made on that. We went to this site as well, looked at it. But I don't know if somebody can pick out from this beam, not from that area, what is so amazing about this. I realized it quite late as well. I didn't realize it, but just if somebody can observe this beam and say what is so different about this beam. So, okay, if you see, this is a partially pre-stressed beam. There's a lot more rebar. It's not a fully pre-tensioned beam. And I bring that this statement with a lot of gravity over here is that very unfortunately UHPC is not being utilized to its potential in the service state right now. We are all designing UHPC as fully pre-stressed, but the fibers are being used at the ultimate state for design. That's fine, that's all. But there is a lot that UHPC can do for you because the fibers are there. Can we design them as cracked, partially pre-stressed UHPC beams?
We need to have more data.
This is a nice point you raised now. Are there program provisions now for these allowable stresses for UHPC?
We have, I think, French and Swiss guidelines are there. But the major problem is, we are relying on the post-cracking behavior strength. As this is ultimate flexion shear we are using.
Yeah.
But scientifically, we don't have a lot of data to really see how is it folding, crack weights, all these things. I mean, 2% fibers are there, okay. But then, you take it upon the creep also 0.2. So the deflection, it'll be high.
But what I'm saying is this is a gap that can be filled through some research, right? And we can actually bring more efficiency into the design methodologies if such kind of a thing is being utilized. Yeah, I mean I realized it quite late myself when I was very closely looking at that picture.
Then you start losing other flexion rigidity.
Yeah, of course. So it's how does the whole moment curvature works initially, and you don't have your eye gross. So
It's an absolutely innovative way to use this.
yeah.
Beautiful.
Yeah. Now this is back in the US for those who have not seen it. I mean, but these are very common, all close to Iowa, right? This one is also in Iowa. The pie girders. I know there's one in New York as well. But yeah, in the initial days they did it, in Iowa. The big advantage, of course, is that you're ready to go. There is no wearing course that needs to be put. You're just simply joining the pie girders. Just that the cost efficiency comes into place over here. Technically, I think this is a wonderful piece of thing right there. And the other thing is what I think, Josie, you're going to be working on, or you've started working on it? Just started working on it. Is this was something that Sriram Maleti and Dr. Sri worked on years back, and now they're picking it up to make it a lot more further efficient. So I think Josie is going to work on that as part of her master's program, right? Wonderful.
That means whatever advantages we get in a conventional waffle slab, say in a building, the same advantages we are trying to bring here.
Yeah, this is a bridge.
It is reduced weight.
Correct. Now, the cost is always a discussion out there, but technically, these things are performing well for the last 15 years or so. I believe this probably was built somewhere around 2006, 7, or maybe slightly later, because the eye girders, the bulb girder came first, and then the pie girder came, and then this one came in. So it has to be slightly later than that, probably. But yeah, 65 mm thick, 200 mm ribs, and you can imagine the amount of rebar that we put in our bridge slab decks, everywhere around the world, right? And here, the only rebar that they had is a 16 mm dia, one rebar in each rib. That is it.
And then the girders are also UHPC?
No, these were conventional girders in this case, but the waffle decks are UHPC with just a single rebar of 16 mm dia going both ways, one each, in each rib. Extensive testing was done. I know that time in 2016 when I visited Iowa State for that convention on the symposium, UHPC symposium, there was one close by, in the precast shop where that was made. So we could actually see those, and then we went to the bridge as well and saw that. And for those having questions about bond, this is a question I get a lot in India. My concrete is M30. How can we put a 150 MPa, UHPC against a 30 MPa concrete? Of course, the theories and all those things, compatibilities, etc., are one part, but the bonding itself is a whole another discussion. And this is out of an actual project. So we did a project for the dedicated freight corridor. And there, the strengthening of the deck was done. So we had a certain roughness. So we took a core out of the deck. We roughened it the same way. We cut it out, we roughened it, and then we poured UHPC. And after the UHPC gained strength, we did the slant shear test, and you can see that the failure is in concrete, it is not at the bond. So, that was quite reassuring that what we had done is providing a good bond between concrete and UHPC.
There is, right now I'm going to recollect the name. A person of your Indian origin is working on this bridge deck rehabilitation using UHPC. Rangarajan, Professor Prasad Rangarajan. Yeah.
I think Rahul also now in the last 2 years we have done a lot of work. Maybe in the evening I'll ask him to discuss.
Yeah, that would be great. Yes,
so you say that water procedure, the surface roughness you have to quantify it.
Yes, that is.
Then you can really improve the performance.
That is the one big thing. Can see the water jetting or the hydro demolition, as we also call it. We do not have a single good hydro demolition equipment in India. There are individual equipments which are there, which are highly dangerous, because the person who does it, because it was done on a recent project of L&T where we did, they brought in 5 people and put individual hydro demolition jets in everybody's hand. One thing goes wrong, his head will be off or his legs will be off, one or the other things. But yeah, amazing. You're working at what pressures? Sorry, 3,000 bar.
Yeah. We also have something like that.
Yeah, you're working at 3,000 bars. So, but there's a good Swedish company that provides these equipments all over the world, and those are robotic in nature, right? There's a robotic in nature, so the person is somewhere out there, and the speed with which they do the hydro demolition is amazing. I've seen them in action, and that is how they are being done in the US as well. That is what is really needed in terms. Even a single good machine would really help with all these overlay problems, because milling is not the best of the solution on the overlays. It's not the best of the solutions. We have done milling, but even jackhammering, it's going to induce cracks which are going to go inside, right? Milling can be done. If you want to take out 40 mm, the first 20 mm you take out with milling, and the rest of the 20 mm you take out with hydro demolition. It's a cost-effective way of doing it. But that's what we do. Do want to show some good architectural work. You see, this is all UHPC. That's a railway station, again in France. Salute to the formwork supplier. Amazing job of formwork. Long cantilevers, etc., and these with the skylights in there. It was really great looking
French
at
suppliers.
French suppliers. And then some fancy odd jobs, you see a lot of them in Denmark. Denmark has actually been most progressive. If you look at the history today, there could be opinions, who came first. But as far as history goes, that Mr. Hans Henrik, he was one of the first ones to work on what we call today as UHPC, and he brought out that UHPC in 1978.
He's a Dane. Was he a Dane? Was he Danish?
Yes, he was a Dane. Yeah, and Denmark has done everything, done and dusted everything that we are trying to do today. 30 years back, not today. They have done everything 30 years, 3 decades back, what we are trying to do today. So the reason I said that somebody might differ with me, because I was making a presentation and there was a German man sitting in the presentation, and I mentioned that, this person from Denmark, was one of the original inventors of UHPC, and he was like, no, it was the Germans. So I said, fine, if there was a French guy, it would be French. So pardon me for it, but you could really make some really nice architectural stuff. In fact, architectural panels, facade panels for UHPC, structurally, I think they deserve a lot of attention, especially for high-rise buildings. And that is where you would see Denmark has done great amount of work. And after that, the French did good work. The US also has a company called as Tactile, T-A-K-T-L.
Tactile.
Yeah, so Tactile has done a good amount of work with composite UHPC panels. It's glass fibers and glass mesh, but amazing amount of ductile, really ductile facade panels out there. And there is...
Facade, it makes a lot of sense.
Yeah, it does. But again, see, when it comes down through the market, I know for 2 years, there have been inquiries about facade to me. And the only thing is, what is the cost against GFRC? GFRC panels, what is the cost against concrete panels? So those are the market, I would say, whatever, you can say, the financial or the economics that govern. But UHPC panels are going to come. I mean, it's going to be on a slightly premium market segment, but they are going to be part and parcel, because there are, the kind of huge constructions that are going around the country, including Hyderabad. In the last 10 years, Hyderabad has grown like crazy, like amazing. And Mumbai itself, I don't know how they are finding space in Mumbai. And an island, they are able to find space after space to build 60-story, 70-story towers, and they are doing that every now and then. But these kind of demands are going to come through. And I say that with conviction, because the prices, the real estate market, the prices are going up like anything. And so the developers are not bothering now to put, the money into all the fancy items and everything. So the market will automatically come. But that's what I wanted to say. I said, we need to add value to the project. UHPC is for that purpose, solve problems, see what you can do against steel and all. There's a lot out to be done, and it can be done. We are finding our ways into segments that we had never thought about. Every month there is at least a couple of calls, and we think, oh, these people are looking for UHPC for their, application, which I had never thought about. One day I walked into a sound and music exhibition, and I was talking at one of the stalls with one of the owners, And he asked me, oh, what are you working in? And I said, well, we are working in UHPC. He said, hold on, Satish. You see this boombox? This boombox, earlier days were made out of wood and all of that. They are now worldwide made out of UHPC because UHPC is acoustically great. I said, excellent. Now I know something. So we get demand for material for machine bases, machine foundations. I already mentioned marine, for security solutions where you're providing banking solutions and vaults and high impact solutions, those kind of things. For abrasion resistance, special abrasion resistant UHPCs.
That's why that deck resurfacing is getting popular because of this vehicular abrasion.
Correct.
It is becoming better than conventional concrete.
Absolutely. So the need for UHPC is coming from very different angles rather than just bridges or building columns or something like that. The only reason I can provide some solutions for building is I'm a structural engineer, so I know I get that benefit of trying to figure out what I can do for them. If I was just a material supplier, probably I wouldn't be able to think of what I can do for them. But with a structural engineering background, I can do that. Similarly, in bridges, it's you have to go longer spans, etc., and that helps. But I believe UHPC has a lot more to offer in the country, and we don't know who those guys are. We need to reach those guys, and those guys don't know they need UHPC, but somehow some places things cross over and it just works out. But thank you very much. Yeah.
Thank you.